It's a huge pleasure to have Noga Alon, who's going to speak to us about random friends walking on random graphs. As usual, if you would like to ask questions, please feel free to raise your hand or to ask them in the chat. That's probably easier. We have both co-authors in the audience, and they sound like they're happy to join in a discussion if necessary. So that's great. Noga, over to you.
Okay, thank you, Christina. It's a pleasure to have the opportunity to speak here, and thank you all for participating. So I speak about random friends walking on random graphs. Hopefully this will make sense in a minute. And this is a joint work with Colin Defant and Noah Kravitz, two bright graduate students from Princeton, whom you see here, and who are also participating. Okay. So this is really something that is an extension of the famous 15 puzzle that I'm sure all of you know. This was invented by Noga Chapman in 1874, so about 150 years ago, and became very popular a few years later, already in 1880. And there is some controversy about the actual invention, and in particular, Sam Lloyd, who was a serious chess player and a famous puzzle writer, a man of many talents, but telling the truth has not always been one of them. So he, in 1891, wrote that actually he invented this puzzle, but it seems he had really nothing to do with it. But he did become famous for offering $1,000 prize for showing a solution of reaching one of the impossible configurations. And actually, all the possible configurations for a generalization of the game with an M by N puzzle was published already in the late 70s, 1870s, by Johnson and Story. And this would also follow as a special case of a result of Wilson that I'll mention soon. So we want to extend it, but before I give you the formal definition, let me give you an example. So here is an example. We would have a graph on which we walk. So here is this walking environment in this example. It's a graph with 5 vertices. And we would have another graph with the same number of vertices, and that's the friendship graph. So here you have a player sitting on every vertex, and you have edges that define a friendship or non-friendship between people, basically if they know each other or not. So you see here a Colin and Noah and myself. This one is Joel Spencer, and this is my daughter Neely. I mean, the picture is from some 30 years ago, but we are still friends. So the ages are between people that know each other, and because Colin does not know Joel Spencer, then they are not connected. Okay, so we have a graph on which we walk, and we have another graph which is a friendship graph. And then what we want is to think about a situation in which we take the various players and we put them on the walking graph, and we put one of them on each vertex of this graph, as you see here. And what they are allowed to do now is they are allowed to swap if they are adjacent in the graph on which they walk, and they are friends of each other. So an allowed swap is what we call a friendly swap, and this is one example that you see here. So this is a swap between Colin and Noah, who are friends, and this is a swap between Neely and myself. And maybe now we want maybe let me go back. So maybe now we want to swap between Joel and Colin, but they are not friends, but still we can simulate this swap by a sequence of friendly swaps, and this will come later. So we make this swap and this one and this one, and you see that the net effect is indeed a swap between Colin and Joel, while everybody else stayed where they were. Okay, so we can now talk about the general definition, which maybe you can guess. And here is this definition. And in this generality, this was actually introduced by Colin and Noah. So we have this X and Y are two graphs, each on n vertices. They have the same number of vertices. And then we defined a much bigger graph, the French and stranger graph of X and Y. So this graph with vertices are all the bijections between the vertices of X and the vertices of Y. And we think about it as a placement of these n different people on the vertices of the graph on which they walk. And then two bijections or two placements of the people on this graph are adjacent if one is obtained from the other by a friendly swap. Okay, and it takes some time to get used to this definition, but I wrote here one example. So in this example, of course, this definition is basically symmetric with respect to X and Y. So you can think about each of them if you want as a graph, as a friendship graph, and about the other one as a graph on which we walk. So if the graph on which we walk is a cycle of length 4, as you see here, and the friendship graph is a star with 3 leaves, then you can convince yourself that the friends and stranger graph is actually 2 vertex joint copies of the cycle of length 12. You see, the only thing that matters is where in this there is this guy in the friendship graph who is a friend of everybody else, and the only thing that matters is where he's sitting, and then he can swap himself with the 2 neighbors. So this is going to be a 2 regular graph, and it's not difficult to convince yourself that this friendly guy can put himself everywhere he wants. And on the other hand, the cyclic permutation between the 3 others cannot change. And this gives us that in every connected component, you would have 4 times 3, which is 12 vertices, and therefore there are 2 connected components. Actually, if you think about it, this is really like the 15 puzzle game, only played on a 2x2 board. Okay, so this is one example. And let me say something briefly about a previous work or about related notions. So the first thing to observe is that for any graph Y, if we take for the graph X, we think about it as a complete graph on n vertices, then this French and stranger graph is just the Cayley graph of Sn generated by the transpositions corresponding to the edges of Y. So, so this is just a some description of the Cayley graph with respect to transposition. Now the 15 puzzle game with which we started. So this is just the friends and strangers graph, where the friendship graph is a star with 15 leaves, right? Because the empty square is connected to everybody else. We can swap it with everybody else. And the graph on which we walk is the 4x4 grid. So this is the 15 puzzle. There is a nice paper of Wilson about which I'll talk a little bit more later. And he studied the connected components of the friends and stranger graphs with respect to the friendship graph is again a star with n-1 leaves. So we have this one vertex, like the empty cell in the 15 puzzle, that is a friend with everybody, and there are no other friendship relations. And X is now a completely general graph. And we want to understand the connected components of this graph. Richard Stanley studied the connected components of these friends and stranger graphs when both the graphs X and Y are a path of length n. So he didn't describe it in this way. He was really defining some equivalence relations on permutation on members of Sn, where two permutations are equivalent if one is obtained from the other by a transposition of adjacent elements that differ by at most one. But this is basically this graph, and the equivalence classes are the connected components of this graph, and he was saying something about them. And Colin and Noah studied, among other things, the connected components of the friend and friendship graphs of a general graph X with respect to a path of length n, and with respect to a cycle of length n for general X. And I'm not going to really talk about it, but let me just mention. So usually when someone says in a lecture that he's not going to talk about something, it means exactly that he's going to talk about it now. So I'll talk about it very briefly. So one thing they showed is that for general graph X, then the number of connected components of the friends and strangers graphs of X with respect to a path Pn is the number of acyclic orientations of the complement of X. And if we are with respect to a cycle of length n, it's a little bit more complicated, but still it can be computed in terms of the Tat polynomial of the complement of X, computed at some point, and it also has to do with the sizes of the connected components of the complement of X. So there are some interesting results here. But okay, and let me say something about some basic properties of this notion, and then we'll consider the problems that we want to discuss today. So here are some basic properties. Let's consider two n-vertex graphs, X and Y. So what are the isolated vertices of this big graph, friends and strangers graphs of X and Y? Well, for a vertex to be isolated, it means that it's a placement of the people on the vertices of X, say, where there is no friendly swap. So exactly it means that there is no edge of X, say, that is connected also in Y, which means that this corresponds to an edge disjoint packing of the two graphs x and y in Ka. No pair is connected in both graphs, and this is if and only if, right? So in isolated vertices, a vertex means that we just picked the two graphs xy in the complete graph Ka. Now, as we said already, this definition is basically symmetric, and the graph with respect to x and y is isomorphic to the graph of y and x. So you just replace each permutation by the inverse permutation, but it's basically the same bijection, the same graph. Well, if x is disconnected, then of course, so is the friends and strangers graphs of xy, right? Because if you have some group of people on one of the connected components of x, then they cannot move by any swap to another connected component because there are no edges that connect them with other connected components. So in fact, there would be lots of connected components of this big graph corresponding to which people or which players are sitting on the vertices or of which component of x. And then there is this parity argument that probably many of you have seen with respect to the 15 puzzle, that if both graphs x and y are bipartite and n is at least 3 to avoid some triviality, then again the big graph is disconnected. And this is because if they are bipartite, so let's think about the friendship graph as boys and girls. So whenever we do a swap, a friendly swap, then we change the parity of the number of boys in the first connected component of x. And we also change the parity of the permutation because that's a transposition. And this means that the sum of the two parities, the parity of boys in the right connected component of x and the parity of the permutation of everything, stays invariant. And because of this, there are at least two connected components. And this is indeed a case with the 15 puzzle where both graphs are bipartite. Let's talk about the star graph, K1 n-1. So this is the generalization of the 15 puzzle, right? So the friendship is we just have one vertex that is, or one player that is a friend of everybody, and there are no other friendship relations, but the graph on which we walk is a completely general graph. So we want to understand when it is disconnected. Somehow the most natural question to consider are the connected components of this graph, because we want to understand from which configuration we can move to which other configuration. So we already said that if x itself is disconnected, then this friends and strangers graph is also disconnected. Now, something similar is that if x has a cut vertex, like you see in this picture, then also the graph is disconnected because, so here is this a cut vertex that is drawn in red here. Now suppose that in the right block, the block to the right of this cut vertex, we know which are the players there. And let's say that this friendly guy, the center of the star, is also on the right side. So he's the only one that is allowed to swap himself with someone else. So he's walking. And if we are trying to shift things from the right to left, then the only way to proceed is that this friendly guy has to locate himself or herself on this red cut vertex, but then he cannot shift anyone else from the right to the left, right? Because if he goes to the left now, then this guy someone from the left will become the cut vertex, but it will not be able to go to the right, and the same. So really, again, just as a case of disconnected X, the identity of the players on the right block and on the left block will not change. Besides the identity of this center of the star. And in particular, the graph will be disconnected. Now, we already said that if X is bipartite and N is a K3, then it is connected because also the star graph is bipartite. So these are two bipartite graphs. Another thing that we already saw by an example, that if X is a cycle of length at least 4, then the big graph has, in fact, exactly n-2 factorial connected components, because in each component, this center of the star, the friendly guy, can locate herself anywhere she wants on the cycle, but the cyclic permutation on the others cannot change. And therefore, every connected component here would have a size n times n-1, and the number of components will be n-2 factorial, which is more than 1 for every n that is at least 4. And there is one additional exceptional graph that is denoted here by Z0. So this is this particular graph. And one can check directly that here the big graph has 6 connected components. Each of them is of size 120. So these are examples when this star graph is disconnected, and it turns out that the converse of this is basically true, and this is what Wilson proved. So that's a nice result. And he proved the following: that suppose we have an n-vertex graph, and suppose it has no cut vertices, so it is two connected, be connected. It is not the exceptional graph, this Z0, and it's also not a cycle of length at least 4. Then, if it is also non-bipartite, then the friends and strangers graph is connected. And if it is bipartite, then this big graph has exactly 2 connected components. Right? So this is and the proof is nice. It's not very easy, and it basically combines or based on the fact that every 2 connected graph has what is called an ear decomposition. So it goes by induction on the number of ears. And then it uses some group theoretic arguments. So we are basically building the symmetric group or the alternating group in each of the 2 cases. And I'll not say more about this. Let me just mention that in all the examples that I mentioned so far, including in the theorem of Wilson, if we want the friends and strangers graphs to be connected, let's say, then the maximum degree in at least one of the 2 graphs so far has to be very big. So either one of them is a star, so the maximum degree is really big, is n-1. And in the other cases I mentioned, when one graph was a path or a cycle, then the other graph had to be a complement of a forest. So really some degree would be n-2. And in fact, it's not so obvious when you first think about it to try to come with an examples of x and y, both having relatively small maximum degree, so that the graph, the friends and strangers graph, will be connected. But this will follow from some of the things that we will discuss soon. So, so here are the questions that I want to discuss, and they both have to do with the connectivity, which is the most basic question here. And I can see actually that there are some things in the chat. So if there are things in the chat that I should, okay, I see. So the only real question in the chat is what is the two connected? So two connected means that there are no cut vertices, namely the graph is connected, and whenever we delete a vertex, it stays connected. Okay, so this is a two connected graph, and okay, so I try to look at the chat from time to time, but I'm not.
We can also answer questions.
Okay.
I was typing an answer, but you got it.
Okay, sure. So please do. Yeah. Okay, thanks. Okay, so here are the questions that we want to consider. So the first two questions have to do with the minimum degrees that guarantee connectivity. And it comes in two versions. So the first question is, what is the smallest d sub n? So this is a degree that is a function of n, so that whenever you take two n-vertex graphs, x and y, and each of them has minimum degree at least d sub n, then the friends and strangers graph must be connected. It makes sense that if the degrees are big, then it is connected. So we want to understand what is the minimum degree that guarantees connectivity. And then we have the bipartite version of the same question, or some bipartite version of the same question. What is the smallest d sub n, so that these friends and strangers graphs of x and y must have exactly two connected components whenever we take two bipartite graphs x, y. Each of them is bipartite with equal color classes, so with classes of size n each, and each has minimum degree at least this d sub n. So this is a one set of or one pair of questions, and here is a second, and here is another one. So after all, this is a seminar on discrete mathematics and probabilities. So we want to have something random here. So we'll really consider random graphs. Suppose that both graphs x, y are independent binomial random graphs in GNP. P could be a function of n. And we want to understand for which P of n is it true that this friends and strangers graph is connected with high probability. So this is obviously a monotone property. And for P that is very small, we expect the big graph not to be connected. And for P that is very big, I mean, at the extreme, both graphs are complete. So of course, then it becomes connected. And we want to understand what is the threshold for becoming connected. And then there is also the bipartite version of the same thing. So we have two independent bipartite random graphs, each with equal color classes of size n, and we want to understand for which P of n. And now, of course, we take it random, we place every edge only if it connects the two distinct color classes. So when is it the case that with high probabilities, this has exactly two connected components? And I tell you something about the results, and then I describe only a little bit about the proofs, but okay. So first, the results about the minimum degree, where I'll not say much about the proofs, but I'll say something about the easy direction of the proofs. So we asked what is the smallest degree D, so that whenever you take two graphs on n vertices, and each of them has a minimum degree at least D sub n, then the friends and strangers graphs must be connected. And one result in the paper with Cayley and Noah is that this maximum degree is at least roughly 3n/5, forget constant, and most 9n/14. So we don't really know the truth. And I just tell you what is the lower bound. That's relatively simple, and we suspect that this is actually the truth. So here is the example that shows the lower bound. These are basically degrees 3n/5 minus some small constant, where the graph is still disconnected, the big graph. So what we take is that the so-called clique blow up of two copies of C5. Namely, we split the set of vertices into 5 equal classes. Let's say that n is divisible by 5. So these are the classes that you see here in light blue. And then we add, so each of them is a clique in both graphs, in both the friendship graph and the graph on which we walk. And then in one graph, we add complete bipartite graphs between every pair of the cliques along one cycle of length 5. And in the other one, we add these complete bipartite graphs between any pair of another complementary cycle of length 5.
I think you're missing an edge on the right.
Yeah, this is true. I'm missing, yeah, it looks, indeed, it looks a little bit right. So, so indeed, here, thank you. So here there should be another complete bipartite graph between this class and this class. Actually, I never know. You do see my mouse here, right? I think, right? Okay, yeah. So thanks. So there should be another complete bipartite graph here, and then you see that basically the degrees are essentially 3n/5. Every vertex is connected to everybody in its own clique, and also to two other neighboring cliques, assuming once we fix this picture. And on the other hand, it is clear that once we decide which players are sitting in this, say, in this clique here, then they cannot move to any other clique. They can move between themselves, but because the two complete graphs that join different cliques are disjoint, then they cannot move to any other clique. So they would all stay there. And because of this, this graph is disconnected, which means that there are lots of connected components. And we could prove an upper bound, which is 9n/14. And this takes quite a few pages. It's probably not tight, and I'll not talk about it. Yeah, so actually, there is no missing this. I just didn't press the right. Okay, yeah. So just my incompetence, but the picture is okay. Good. All right, and the bipartite version of the same question is there we understand things better, and actually we know the precise answer in 3/4 of the cases, sort of, and almost the precise answer in the remaining case. And here really is a correct answer is about 3/4 n. And again, I'll just show the lower bound and let me here be better in showing you the right picture. So here the bipartition in the left graph is the left side and the right side, and the bipartition in the right graph is the top and the bottom. Each of the 4 parts are equal. Now each of the 4 light blue things is an independent set. The green graphs are complete bipartite graphs, and the yellow graphs are graphs with density half, and they are chosen in such a way that each yellow graph on the left does not share any edges with each corresponding yellow graph on the right. And then you can convince yourself that every degree here is about 3/4, right? Because a typical vertex is connected to all the vertices in n/2 here, and half the vertices in the other n/2 there. And these 2 graphs actually pair. They don't have any common edges. So this is an isolated vertex, and because of this, the graph, the big graph is disconnected, and the proof of the upper bound again requires some work, and I'm not going to talk about it. So I'll try to tell you a little bit more about the case of random graphs. So the first version of the question was that if x and y are independent binomial random graphs in GNP, and we wanted to know which probability is a threshold for making the Francis-Spencer graphs connected with high probability. And the result is that it's roughly 1/√n. Well, up to little o1 in the exponent, but still it gives essentially the correct value. And you see that in particular, this will give us examples of graphs in which the maximum degree is pretty small, is only square root or roughly square root n, and still this Francis-Spencer graph is connected. So this is a result here. And there is a corresponding result for the bipartite case, and there actually we don't have a tight bound. The lower bound is something like 1/√, and the upper bound is up to logarithmic factors 1/(n⁻³ and it will be interesting maybe to find out the truth. So these are the results for the random case, and I want to tell you a little bit about the proof. And again, one side, the lower bound is very simple. So we want to show that, so now I'm talking about the non-bipartite case, and we want to show that if the edge probability is only some constant over √n, then with high probability, the big graph is not connected. And in fact, it will have isolated vertices. And this is simple, because if the edge probability is less than what is written here, 1/√2√n minus a little bit, if you want, then the maximum degree of each of the graphs with high probability is less than √n/√2. And we have this result of Sauer and Spencer about pecking graphs. So actually there is an old conjecture of Bolobash and Elbridge that says that conjectures that if the product of the maximum degrees of 2 graphs on n vertices is at most n+1, that they can peck. This is not known, but something almost the same is known is that if twice the maximum degree of x times the maximum degree of y is less than the number of vertices, then the two graphs take. So here, just with high probability, each maximum degree will not be too big. This inequality will be satisfied, and then we will be able to pick the two graphs. We have isolated vertices. It will not, the graphs will not be connected, and this gives the lower bound. So P has to be at least some constant over square root n. And of course, the more interesting part is the upper bound. So this is the main part of the proof, is to show that if the edge probability is at least, and I wrote here something explicit for the error term, but this is not, certainly is not tight. So if specifically P of n is bigger than something exponential in log n to the 2/3 over square root n, then with high probability, the friends and strangers graph is connected. And the way to show it is to show that if this is the case, then with high probability, whenever we have a bijection from the between the vertex set of x and the vertex set of y, namely a placement of the players on the graphs, on the vertex of a graph on which we walk, and then for any pair of adjacent elements in the graph on which we walk, then this pair is exchangeable. So they are exchangeable in the same sense that Colin and Joel Spencer were exchangeable in the original examples that I showed you in the beginning. Namely, we will be able to have a sequence of friendly swaps so that the net effect between them would be to swap U and V and to keep everybody else as they are. So if this is the case, then whenever we have a given bijection, a given placement of the players on the vertex of Y, and we want to swap an adjacent pair in Y, then we can do it. And then by a sequence of such swaps, we can actually see that we can swap every pair of vertices of Y because Y is connected, so assuming that Y is connected. And if we can do this, then indeed we can realize any permutation, because every permutation is just a product of transposition. So it's enough to show that we can do this, and let's try to see how this is possible. Again, I see that there are some things on the chat, but I see someone is taking care of it. If I have to stop and respond to the chat, then tell me, Holly and Noah, if you see something that. Okay, so here is a first attempt to try to establish these things that every pair of adjacent vertices of Y with respect to any bijection is exchangeable. So it's a first attempt, which means it probably it's not going to work, but still, let's look at it. So suppose we want to swap U and V. Now we could hope maybe, and for some edge probability this would work, that for every adjacent pair U and V in Y, there would be some common vertex W, which is a common neighbor of U and V in Y, and the vertex W prime, which is mapped, which corresponds in the bijection. So what we see in the right is what happens in the graph X, and what we see in the left is what happens in the graph Y, and the prime exactly corresponds to the vertices that are mapped to the corresponding vertices between X and Y. So W prime is mapped to W, U prime to U, and V prime to V. If for this pair U and V, we would have a W that is a common neighbor of them in Y, and W prime is a common neighbor of U prime and V prime in X, then this would be fine, because then we would just be able to swap W with U, and then W with V, and then W with U again. By 3 swaps here, we would be able to really exchange between U and V. But the trouble that this, of course, fails miserably for every sparse graphs, because if the number of common neighbors of U and V in each of the graphs is less than n/2, then there could be some bijection so that no common neighbor of U prime and V prime in X is mapped to a common neighbor of U and V in Y, right? Because we have only n/2 or less than n/2 vertices in each such set, so there could be a bijection when they are mapped to disjoint sets. And for this, P has to be very big. So this does not work. Let's try a second attempt. So here is a second attempt that is better and also enables me to explain what is really being used in the third attempt. That would be the best ones that we know. So suppose that for every pair of vertices U and V that are adjacent in Y, we have the left configuration in Y and the right configuration in X. And again, every prime thing is mapped to the same thing without the prime. So we have this configuration in X and this configuration in Y. Now, why do we know that this would be enough? So these are small enough graphs, and if you want, you can just find out some sequence of swaps that would really just exchange U and V and keep everybody else in their position. But I'm saying that actually we don't have to think about it or to do it because this actually will be enough, will suffice by Wilson theorem. You see the graph on the right here is really a star graph in which the center is W prime. So one of our graphs is a star. Now the other graph is two connected. It's connected and doesn't have a cut vertex. It's not bipartite because it has, for example, a cycle of length 5. It's not a cycle, and it's not this exceptional graphs that we saw, which had 7 vertices. This graph actually has 6. So this means that we know by Wilson theorem that we can realize if we just ignore the rest, all these configurations appear in a small part of the two random graphs, but we ignore everybody else. We are not going to move them at all. And we just look at these two small graphs. On these small graphs, by Wilson theorem, we can realize any permutations that we want. So in particular, one thing that we can realize is to swap U and V and to keep everybody else in place. And this will be good enough for us. Now, the good thing about these two graphs here is that, for example, we don't want any common neighbor, any neighbor of U in the left graph, so that the corresponding vertex in the right graph is also a neighbor of U, because this has to exist for every bijection. So just as before, if the typical degrees are less than n/2, then there are always some bijections so that no vertex will be a neighbor of U prime in X and will be mapped to a neighbor of U in the other graph y. So we really need to choose some graphs so that there are no, so that they look more or less like this. And because they look more or less like this, then we can apply, so I wrote it here, we can apply the Jansson inequalities in union bound, and I'm not going to show how the computation works and what exactly you're doing, but this is not too complicated. And you can see that if the degree here is a little bit bigger than 1 over n to the 1/4, so still not what we want, then this will hold with high probability, namely for every 2 adjacent vertices u and v in y, and for every bijection, so the union bound will be over all these bijections and over all the pairs u v, there would be such a configuration, and but this will definitely fail with high probability for the p that we want. So what is the construction that actually works for what we want? We need some more complicated graphs. In particular, their size has to grow as a function of the size of the graph. And this is one picture of a configuration that works. Here, the 2 vertices to be swapped, what was u and v before, are now denoted by m+1 and m+2. They are denoted in red here. And m grows with n, so maybe it's log n to the 2/3. And not everything is drawn here. So basically, the red arcs here have lots of vertices on them. And all the vertices that you see here, all the x's and all the y's and the z's that are not marked here, and w appear, I mean, their images appear somewhere here on the cycle. And they also have to appear so that they are far from each other and far from the z's. But let me just say that so maybe again, the proof of exchangeability will apply Wilson theorem several times. And again, I'm not going to show it, but the important thing is that to realize it is that when you delete here this m+1 and m+2, the 2 vertices to be exchanged, and you delete them here also, then the graph that is left here is a star. So it looks like in the Wilson theorem. And the graph that is left here is 2 connected and not bipartite, because we choose it not to be bipartite. So this and not a cycle, so it satisfies the Wilson theorem. And it also it is also important that when in the left graph here we delete the vertices z5 and z11, so these are 2 other vertices, but now we don't delete m+1 and m+2, then also what is left is a 2 connected graph that is not bipartite and that is not one of these exceptional things. And because of this, it means that we can apply Wilson theorem several times and somehow shows that we can keep, by a sequence of moves, we can swap m+1 and m+2 and keep everyone in place. And here, if we apply in the right ways Jansson inequalities, then it will give us the statement we want. And I'm not going to show anything more about this. Let me just say that for the bipartite case, it's a little bit more complicated, and we actually don't have a tight bound because we don't have the right analogs that is needed here of the Wilson theorem for the bipartite case. But we were finding some finite graphs by computer search, and these are basically the graphs that are being used. and they give the upper bound. The lower bound is basically proved just as before. Let me finish by mentioning a few open problems. So first, we believe that this 1 over square root n essentially is a threshold for the bipartite case as well, to get two connected components. So this will require some argument. Now there was a gap in this value of the minimum degree that guarantees connectivity that I mentioned. We had the gap between the lower bound and the upper bound. We think that the lower bound is essentially the truth. So this is this 3n over 5. We wonder if there is a heating time result, like the results in the usual random graph theory literature about the random graph process. Suppose that we start with two empty graphs, no edges, on n vertices, and then we generate a sequence of pairs of graphs every time we add the random edge to x and the random edge to y among the edges that we didn't take so far. And we can look at the first time in which this big graph does not have any isolated vertices, okay? And then we can look at the first time in which the big graph becomes connected. And one wonders if with high probability, these two times are the same. And if not, are they essentially the same? The proofs that we know only shows that the connectivity one is not much bigger than the other one. But we don't even know if they are of the same order of magnitude. There is some factor, so this will also be nice. Here's another question, and this is in general about the friends and stranger graph. Is it true that always every connected component of this graph has small diameter that is only polynomial in n? This could be true as far as we know, always. And maybe another property is to try to take a random walk on the big graph and to understand the mixing properties. And I wrote here that if one of the graphs is a complete graph, this is something that corresponds to Aldo's spectral gap conjecture, on which there are some nice results, but I'll not talk about it. So this is just mentioning it to those who know it. And let me just finish with an animation copied from the presentation of Colin and Noah. And this is this thing here. I have to know where to stop. I think it's here. Right. So thank you. Mm-hmm.
Thank you for a lovely talk, Noga. Can I invite anybody who would like to ask a question to either raise their hand or to say in the chat? Alex has a question. Alex, go ahead.
Yeah, Noga, thank you for a lovely talk. So I have one question, which is if you're given one of these graphs, and I mean the two graphs and two bijections between them, can you tell in polynomial time, is there an efficient algorithm for determining whether you can get from one configuration to another?
Right, yes, so the complexity question is also interesting, and I don't know it in general. I have to think a little bit, but let me say that definitely we know that some questions of this type are hard. So, for example, given two graphs, to know the number of connected components of this graph is NP hard because it corresponds to computing the top polynomial of something. So at least some complexity questions that are related are hard, and I would expect that this one is hard as well. since we don't know the result, the question about the diameter, then what you asked, it's not even clear if it is in NP, right? So it's not even clear if I could convince you that they are in the same connected component, even if they are, because maybe the diameter is big. But so it means I would expect, but one has to think about it, that it should be at least NP hard and maybe even harder. But it was a long answer to say that I don't know. Right.
Thank you.
Okay.
Does anybody else have a question? I can't see any raised hands, and I can't see anything else in the chat. So what I'm going to suggest is that I stop recording.